Good evening, Professor, and I want to thank you for this time you've given me. And I want to say at work, I had a very big issue with the disk subsystem, and we were getting heavy weight events on one of our disks for the queries. So it's not a query problem; it's a massive storage problem that we face. So still, we're working on it. Even this holiday, I have to log in again to see the findings. So, Professor, I want to thank you for this time. And I want to say that this project was not easy with graphs. And I, in fact, wrote down all my points here because that's how many things I learned from this project. The first thing is that Python implements DQ as a generalization for both stacks and queues. So instead of having a different stack implementation, different queue implementation, they've used the same data structure called DQ. And if you do a pop left, it implements a queue, and if you just do a regular pop, it implements a stack. So that was quite unique because I went online to search for stacks and I didn't find anything. Then I came to know that they're using the same data structure. Second thing, the recursion. Um, we can implement BFS and DFS using recursion, but there's no way we can keep count, of the height and leaves. And that's what I found. It was so difficult to keep track of the height, especially for depth first search, because the left heights are totally different from the right heights. It was very difficult. And also for BFS, for displaying trees, it was very difficult to display because you have to display at the same level. And for that, you have to keep track of how many children we have at each level. So that was very tricky. So I took hours to figure it out. But finally, I did it in one line. But that one line took hours of complex analysis. Next, the DFS is in DFS very difficult to find the height, and and also it's very difficult to yes, the order of the left node and right node insert into the stack to push them into the stack. That determines whether it's a pre-order or an in-order or post-order traversal. So based on what I've done, it's pre-order traversal, and I'll show you how. So let's get to the actual work. Let's show some actual work. So I'm going to share screen. I'll make sure I do it. Okay. Here you go. Share the whole screen. Yes. Right. So I'm sharing the screen. I'm opening up my prompt, and I'm going to show you. This is my virtual machine, and if you look at my thing, my files, you can see that how I progressed from version 2 to version 3. It wasn't easy at all, and finally I converted the BFS to DFS. But I'm going to show you that the BFS itself, there's a lot of depth in the BFS. The breadth first search itself was not easy to implement to display the values on the same height. And I want to say that in DFS, I used the BFS, but I used the stacks. But even there, calculating the height, computing the height was very tough, Prof. So I'm going to show you how I did it. So I'm going to open it. Here's the tree, left child, right child, and here it is. So you have BFS. Now, don't be fooled. This code looks simple, but it was very complex to analyze. So you have height here, and then you have this. You have the length of traversal queue, and here's something I added. It's just to print the height. I had to find out for all the values in the traversal queue. I was going to pop left, print it, then I was going to pop, then to append, and then do left and right. Then if it did not have a left or right node, I'm going to say it was left, right, leaf node, and I was going to add the number of leaves. So this line would compute the number of leaves. Now this addition, I added this. This is not part of the regular BFS, what do you say, queue and program. And if you look online, you may not see it because I added this to compute the leaf nodes and the height. Because I don't want it to go at each level and do a height plus one. I wanted to do it for all the values at that height. So this length of traversal queue actually pushes in the number of nodes at that height. So then from here, I want to do a height plus one only after doing all the values. So let's say there were like two children. I wanted to go to the first child, then I wanted to go to the second child, and only then I wanted to increase height, because if we increased height here and here, we'd get an abnormal number of values. So this took a very long time to actually code. Though it looks simple, it's very complex. Then finally you do a list of nodes. So that's the complete list, but only thing is it's in kind of order, and you have a number of leaves and height, and then returns it. Okay, so I want to show you this. Okay, or we can go DFS. And in DFS, it looks very similar, but it's totally a different ballgame. It's an entirely different structure. So here again, we use DQ. So there's no separate data structure called stack for in Python. It just uses DQ, and all we're doing is we're doing a pop, and here we're doing a left pop. Pop left. Yeah. So and it's very brilliant because you're using a same structure, and you can also reverse the nodes. You can play around with the structure. So they have implemented it very well, for stacks and queues. Now here is saying, okay, so as long as the stack is not empty, you're going in, and for that range of stack, you're popping, then you're increasing the left height. So this is what I did. Instead of just having height, I had a left height and a right height. So as the left nodes were being inserted, I put a left height, and as the right side nodes were being right side, and finally I print the leaf node, okay, and leaf node and this times one, and I did a max height. It's not really required, but the thing is, the height equals the left height, right height minus left height minus one, and that gives you the height, which is the same as the height in the BFS, but the computation was totally different. And you see, this is, I've also noted, this is a pre-order traversal. So you visit the parent, the left and right child. So what it does is, because you're visiting the left child first, it puts the left branch right at the bottom of the stack, and then it first pops out all the right values. So it's like, let me finish off the whole right section, then let me go to the left section, and it's very difficult to keep count, and you don't know which level the leaves are, the left node is at. So finally I had to use this computation. So it computes all the right minus left, and it gives you the branch. And okay, so now this is it. So let's see how it works. I say Q, and I'll just go by this one. So load CSV. Let me do random number CSV. That's our file. Okay. Yes. So here we have CSV this. So it pulled in the values just as it were. It's not doing any sorting, right? So now I'm going to sort using BFS, and very clearly I've demarcated BFS versus DFS. So I'm going to say BFS. So I'm doing the BFS, and there you go. Okay, so it's now I'm going to see, it's here, it says leaf count 31, height 14. I'm going to show how it does it. Let's go a little up. Should we go a little up? Okay, yes. So here it is, length of traversal Q1. So we're starting off with the root, and then we're putting all these values and coming to the leaf. Now remember, this is not the height, and what I want to say is that all these, oh, actually, wait a second. All these are at a certain height, correct? No, 3, 1, 4, no, something. Yeah, these all come at a certain height, and then this comes height 2, height 3, height 4. Probably this should have been on a different line, but but the computation is correct because it shows exactly the leaf nodes, exactly where they are, and finally comes, and then it has a node count this, and it has a height this. So this was very tough to print on also on the same line. And this is the level, yeah, level 1, level 2, level 3. This is the root. Yes, this is the root. Yeah, it should have been on another line, but that's how it did. So I was able to separate. Otherwise, you get all the numbers on one line, so it has to know where the height is, so this was very difficult. And because I had that intermediary for loop, we were able to do it for all the children in that node, and okay. And now, so that's let me reload. I don't want to use the same data structure, so let me again go to random numbers. Let's see, CSV. Oh, okay, it's loaded. So again, is it the same? See, this is, oh yeah, at the end you get a structure that's a totally sorted structure in a binary tree, so we don't want to use that. So that's why I reloaded. Now I'm going to say 3, Okay, so yes, so what I did was, this is what I did. Oh, right, let's go. So DFS, narrative stack, so this is here. So it comes all the way, it goes to leaf node, leaf node, leaf node, leaf node. So choose the leaf node. Then here, leaf node. So here the list of leaf nodes, right? So you have all the left leaf node count, then you have the left height and right height, and you do right minus left minus one, and that gives you the height. That's a traversal. So this is a tough, very tough computation. Um, so thank you very much for your time, Prof. It's very useful, and I wanted to learn it, and it wasn't easy, Prof. So I thank you for this time. Yeah, thank you.